We're now going to have a look at what's called L'Hopital's rule for calculating limits. This uses differentiation to calculate limits in a particular way. Consider the function sine x over x as x tends to 0. We've had a look at this function before, and we know that the function tends to 1 as x tends to 0. But how do we calculate this? In particular, note that as x tends to 0, this is tending to the form 0 over 0. Of course, 0 over 0 doesn't mean anything in and of itself, but we can write this to represent that this limit is of the form 0 over 0. This is called an indeterminate form. If we have two functions f and g, then we can calculate the limit as x tends to a of f of x over g of x as follows. Because the functions themselves are tending to 0 as x tends to a, I can write f of x as f of x minus f of a because f of a is 0. Similarly for g. Why do I do that? Well, bear with me. If I write the numerator and denominator as follows. If I divide the numerator and denominator both by x minus a, then using rules for limits, I can see then that this is equal to f prime of a over g prime at a, provided this limit exists. And so I can then write this limit of f of x over g of x as the limit as x tends to a of f prime of x over g prime of x. And this trick only works for indeterminate forms because we had to add on these bits as they go to 0. This is known as L'Hopital's rule. So let's try this on the function sine x over x. So this is of the form 0 over 0, so I can use L'Hopital's rule. So what I do is I write, this is the limit as x tends to 0, the derivative of sine x over the derivative of x. Note that it's not the derivative of the whole function. So I differentiate the numerator, which gives cos x, derivative of the denominator gives 1, and this is a perfectly well-defined limit as x tends to 0, which is just 1. It actually also works on limits of the form infinity over infinity. This is also an indeterminate form. Infinity over infinity doesn't mean anything in and of itself, but if I have a functions f and g such that f is going to infinity and g is going on to infinity, then I can use L'Hopital's rule to evaluate the limit as x tends to infinity of f over g. So an example of this is of the form infinity over infinity, an indeterminate form. We can use L'Hopital's rule in exactly the same way, although the proof of it is a bit more complicated. So as x tends to infinity of e to the x over x squared is a form infinity over infinity, I can still use L'Hopital's rule in this case. So it works for indeterminate forms in this case, and I write the derivative of e to the x is e to the x, the derivative of x squared is 2x, and as x tends to infinity, both the numerator and denominator are still both heading off to infinity. However, because it's of the form infinity over infinity again, I can use L'Hopital's rule once more. Derivative of e to the x is still e to the x, derivative of 2x is just 2, and now I can take the limit as normal, and we see that this is infinity. We can use L'Hopital's rule in other ways. If I want to calculate the limit as x tends to 0 of x times log x, this is now of the form 0 times infinity as x tends to 0. X is going to 0, log x is heading off to minus infinity. So L'Hopital's rule does not work straight away out of the box here. But what I can do is I can use the following trick. If I write x as 1 over x, then the numerator is tending to minus infinity and the denominator is tending to plus infinity. So this is now of the form infinity over infinity, and I can use L'Hopital's rule on this ratio. So the derivative of log x is 1 over x. and the derivative of 1 over x is minus 1 over x squared. Simplifying, this just becomes minus x, and the limit as x tends to 0 of that is just 0. And we can see what this function looks like near the origin. We can sometimes use this to simplify limits when we have infinity minus infinity. We don't know what that's going to go to in general, but with a bit of simplification we can figure it out. Let's try the following. Let's calculate the limit as x goes to pi by 2 from the left-hand side of sec x minus tan x. These are both heading off to infinity, and so we have infinity minus infinity is the form. We can't use L'Hopital's rule at the moment, but we can simplify this. If I write this as 1 over cos x minus sine x over cos x, I can simplify this to 1 minus sine x over cos x. And now, because this is of the form 0 over 0, as x tends to pi by 2, I can now use L'Hopital's rule straight away. So this is then the limit as x tends to pi by 2 from the left of the derivative of the numerator, which is just minus cos x, divided by the derivative of the denominator, which is minus sine x. And that's just 0. So L'Hopital's rule is a nice way to calculate limits of indeterminate forms. When we have indeterminate forms of 0 over 0 or infinity over infinity, we can use L'Hopital's rule out the box. For other types of limits, we may have to do a bit of fiddling around with them first. As a final example, we can look at indeterminate powers. These are when we have limits that are looking like the form 1 to the power infinity, infinity to the power 0, or 0 to the 0. All of these types of limits depend on how they're approached in order to determine whether they're heading off to infinity, minus infinity, or some finite number. Let's have a look at an example of x to the x as x approaches 0 from the right hand side. Now this is strange in two ways. Hard to understand what's happening because 0 to the power x, where x is any positive number, equals 0 for all x greater than 0, and x to the 0 is equal to 1 for all x greater than 0. So what happens then as we approach 0 from the right of x to the x? It's really not clear. The trick is to use logs and exponentials in a sensible way in order to simplify it into a form where we can use L'Hopital's rule. Let's see how to do that. What I'm going to do is I'm going to write x to the x as e to the logarithm of x to the x. And I can do that because x to the x is always positive as we're taking the limit from the right. Now I've done that, I can use the law of logs to simplify. And we've already seen that x times log x as x is approaching 0 is tending to 0. So this is just tending to e to the power 0, which is just 1. So that's a very neat trick that you can use for all sorts of different types of indeterminate powers.